Hello! Today's video is on temperature dependence of equilibrium constants. Most reactions are temperature dependent. To be able to optimize conditions for a reaction, it's important to be able to understand its temperature dependence. An equilibrium constant is a constant for a specific reaction at a specific temperature. You change that temperature, often you change the value of the equilibrium constant. After watching this video, you should be able to relate the temperature dependence of equilibrium constants to Le Chatelier's principle. Remember, higher temperatures like adding heat, and so for endothermic processes, that would be adding reactants, and that pushed the reaction to producing more products. You should be able to predict whether the equilibrium constant will increase or decrease with increasing temperature, and we'll see that for endothermic processes, the equilibrium constant increases with increasing temperature. For exothermic processes, the equilibrium constant decreases with increasing temperature, and again, we can understand that using Le Chatelier's principle. And given the equilibrium constant at one temperature, you should be able to calculate it at another temperature, and you actually just need the change in enthalpy for the reaction. And so equilibrium systems are dynamic and reversible. At the atomic level, they're dynamic. You have reactions constantly going. And so once you reach equilibrium, it seems like the concentrations are constant, but you still have the forward and reverse reactions. It's just that the rate of the forward reaction equals the rate of the reverse reaction. The reversible, because you can go forward with the reaction or you can go reversible with the reaction. That's why we use the two double arrows to denote equilibrium reactions. And so the reaction that we're looking at here, we have a cobalt hexahydrate with two chloride complex forming cobalt with a tetrahydrate and two chlorides. And so the reactants are pink and the products are blue.
At room temperature, a solution of cobalt chloride is pink in color. When we heat it, it gradually turns blue. If we then cool the solution in an ice bath, it turns pink again. The reaction reverses.
But it's kind of cool. We can actually do this reaction backwards and forwards multiple times, and it constantly goes from pink to blue, pink to blue, pink to blue, etc. just by changing the temperature. And so for this reaction, at high temperatures, the products are more stable. They have lower free energy than the reactants. At low temperatures, the reactants are more stable. They have lower free energy than the products. And so at high temperatures for the reaction, delta G naught is less than 0. The equilibrium constant is greater than 1. At low temperatures for this reaction, delta G naught is greater than 0, and the equilibrium constant is less than 1. And so we can ask ourselves, is the reaction as written exothermic or endothermic? And so again, if we think about it, if the products are more stable at high temperature, then the heat must be a reactant. Remember, higher temperatures like adding heat, and so if heat's a reactant, that would push the reaction to producing more products, and so this reaction must be endothermic. But it's really kind of cool if we think about it. At low temperatures, the minimum, the most stable configuration is close to the reactants, and then as you raise the temperature, that minimum actually moves over to the right until it moves closer to the products. And so as you're increasing the temperature for this reaction, the equilibrium constant is increasing. We can look at a different reaction. And so here we have 2NO2 going to N2O4. The NO2 is brown and the N2O4 is colorless.
Nitrogen dioxide, a reddish-brown gas, is formed when nitric acid reacts with copper. The gas is poisonous and must be handled carefully. Even small quantities can cause irreversible lung damage. In a closed system, nitrogen dioxide exists in equilibrium with dinitrogen tetroxide, which is a colorless gas. At a given temperature, specific concentrations of each gas will be present in the system. When the tube is chilled, the concentration of dinitrogen tetroxide increases, and the concentration of nitrogen dioxide decreases. When the tube is heated, the concentration of reddish-brown nitrogen dioxide increases, while the concentration of dinitrogen tetroxide decreases.
And so at low temperature, it's closer to the colorless, and so that means the products are more stable. At high temperature, we have the brown gas, and so that means the NO2 would be more stable. And so again, if we think about it, high temperature, the reactants are more stable in this case, and so heat must be a product. Again, Le Chatelier's principle, higher temperatures like adding heat, If it heats a product, that would cause the reaction to produce more reactant. And so this must be an exothermic reaction. Now we can actually learn more about this reaction looking at its delta S and delta H values to better understand the temperature dependence. Now you should also remember that we can actually determine the temperature at which the reaction goes from being spontaneous to non-spontaneous. If we take the delta G equals delta H minus T delta S, and we solve for T when delta G equals 0, when delta G equals 0, that's the transition temperature, the temperature in which the reaction goes from being spontaneous to non-spontaneous. And so using that equation, we can actually determine at what temperature it makes the transition. And so T equals delta H over delta S. Now you got to remember that typically delta H is in kilojoules and delta S is in joules per Kelvin. And so we have to either change delta H to joules or delta S to kilojoules per Kelvin. And so in this example here, I changed delta S to kilojoules per Kelvin. And so the kilojoules cancel and we're left with 1 over Kelvin, which is a Kelvin. And so for this example, we get T equals 324. And so at 324 Kelvin, delta G equals 0, the reaction is called reversible, and the Ekman constant is equal to 1. Now, at higher temperature, delta G naught is greater than 0. We call it a non-spontaneous reaction. K is less than 1, and it's reactant favored. That's why at higher temperature, we have more of the reactants, as we can see from the picture. Below 324 Kelvin, delta G naught is less than 0. We call it spontaneous. Again, in this context, spontaneous does not mean instantaneous. It means it occurs without any outside intervention. K is greater than 1, and it's called a product-favored reaction. And so again, if we look at free energy as a function of reaction quotient, the minimum is closer to the reactants at high temperature. And then as we reduce the temperature in this case, that minimum actually goes over to the right. And so above 324 Kelvin, the minimum is closer to the products and our K is greater than 1. Now delta G naught equals minus RT natural log K. And so we can solve for K, and K is equal to EXP minus delta G over RT. Remember, EXP is just another way of saying E to the power. And so K is equal to E to the power of minus delta G over RT. And so given delta G naught, we can actually calculate K. Given K, we can calculate delta G naught. Now we can do some math because math is fun, and so K is equal to EXP minus delta G over RT. We've seen previously that delta G equals delta H minus T delta S, and so we plug that in for the delta G, and it gives us K equals EXP minus delta H over RT times EXP delta S over R. Now e to the power of A times e to the power of B is equal to e to the power of A plus B. And so that gives us K is equal to EXP minus delta H over RT plus delta S over R. Now if we take the natural log of both sides, that gives us natural log of K is equal to minus delta H over RT plus delta S over R. And so I want you to pay attention to these two reactions. We'll plot them in the next slide. And so we can see that if we plot K, the Ekman constant as a function of temperature, we get this nice exponential. Now, if we take the natural log of K and plot it as 1 over T, we actually get a straight line. And so you should recognize that natural log K minus delta H over RT plus delta S over R is actually the equation for a straight line. Here, we're plotting natural log K versus 1 over T. And so it's really kind of cool. If we assume delta H and delta S are temperature independent over this temperature range, we can plot natural log K over 1 over T. We get a straight line. The slope is equal to minus delta H over R, and the y-intercept is equal to delta S over R. And so this is one way you can actually calculate delta H and delta S, is just by plotting natural log K over 1 over temperature. But again, in this analysis, we're assuming delta H and delta S are temperature independent over that temperature range. Now, if we take that natural log K equals minus delta H over RT plus delta S over R, and again, if we assume over the temperature range that these are delta H and delta S are temperature independent. And so we got two equations. That's all K1. K at temperature 1 is equal to minus delta H over RT plus delta S over R. Natural log K2 is equal to minus delta H over RT2 plus delta S over R. And so again, just the same equation, but twice because we're looking at two temperatures. Now if we subtract one from another, that gives us natural log K1 minus natural log K2 equals those things. Now notice that the delta S over R terms cancel because again, we're assuming delta H and delta S are temperature independent over this temperature range, and it gives us natural log K1 minus natural log K2 equals delta H over RT2 minus delta H over RT1. And natural log K1 minus natural log K2 is equal to natural log K1 over K2. And we can also take those delta H and the R out. And so we get natural log K1 over K2 is equal to delta H over R times the quantity of 1 over T2 minus 1 over T1. Now you got to be careful on this equation because sometimes people will derive it slightly differently. And so this is exactly equivalent to having minus delta H over R times the quantity 1 over T1 minus 1 over T2. And so sometimes you can put the minus in front of the delta H and then you have to swap T1 and T2. Or I can do it as I did. That's exactly equivalent, but please don't get confused. But this equation is fairly important. This is actually how you calculate the Ekman constant at different temperatures. And so this is referred to as the Van Hoff equation. And again, most reactions, the Ekman constant is temperature dependent. And so if you want to calculate the Ekman constant at a different temperature, you need to know the delta H. And this is how you do it. And so temperature dependence of Ekman constants, very important, very cool. You can calculate using Van Hoff. Enjoy.